Hey everyone, welcome to a video on the shell balance approach. We're going to be talking about what the shell balance approach is, and we're going to be going over two examples. So let's get started right away. Great. So the first thing is, what is the purpose of the shell balance approach? So let's start with what we do know. We do know the macroscopic view. This is what we've been doing for the past several weeks. We've been analyzing bulk flow and finding the average transport variables and their change with their time. So that's such as mass, we have concentration, velocity. But now the shell balance approach allows us to look at a more microscopic view and understand how the transport properties that we've been looking at vary with actual position. X, Y, Z, we can also look at R, theta, Z, in cylindrical coordinates. So we're going to be taking a look at the microscopic view now. And here are some examples of our one-dimensional flow problems that we'll be looking at. So we have both rectangular and cylindrical coordinates. So we have viscometers over here. Some examples are the capillary or the sliding plate. We have circular tubes. We have flow through parallel plates. We have blood vessels modeled through the circular tubes. We have medical device tubing and so many more applications. So let's get started. What is the shell balance approach? So there are 6 steps that you're going to follow to actually perform the shell balance approach. And this starts with number 1 being selecting an appropriate fluid shell. We'll talk more about this in a moment, but we're going to be using a shell rather than the entire system that we're examining. Great, and then we're going to be applying the second step is to apply the conservation of mass to the fluid in the shell specifically, not the entire system. So conservation of mass is something we do know. And then the third step is we're going to apply the conservation of momentum to the fluid in the shell. Then we're going to be applying the relevant fluid constitutive relation to the shell balance approach. And then we're going to be computing the velocity profile using appropriate boundary conditions. So we've touched on boundary conditions, and we'll see how those play into actually calculating that specific velocity profile. And lastly, we're going to compute flow rate Q, and then we have wall shear stress tau and maximum velocity V max, and we'll be able to compute those as well with the velocity profile. Great, so our first example for today's video is blood flow in a film oxygenator, which is using rectangular coordinates, right? So we can see this right over here, and we're going to just be going over some of the conditions of this problem. So blood is pumped at a constant rate over plates with width W and length L. Then we have plates surrounded by an oxygen-rich gas at a constant pressure and temperature, P and T. Great, and then we also have the plate inclined at an angle alpha with the horizontal. So this is also key because it's not just flat, right? There is an incline, so that kind of hints at gravitational forces. We're also given that the fluid is incompressible. And lastly, we're going to assume that blood is Newtonian for this example. Great, and let's get started. So we have our objectives of using this approach, our shell approach. The first is to obtain the specific velocity profile. The second is to find the distribution of shear stress. And lastly, we're going to determine the total blood flow rate, Q, as a function of film thickness, H. So that is one of the unknowns we have right here. Great, so let's start by actually applying the shell balance approach to this problem example. So number 1 is to select an appropriate fluid shell. So let's take a look at the problem right over here. We can see right over here that our goal is to find an infinitely small point, essentially. So we're going to be using a box as our fluid shell, but ultimately we're trying to get down to this infinitely small shell, which is just shown by this dot right over here. So that's the goal. So let's actually put this right over here, and then we have our shell right over here. So we have X and then a change in X denoted by X plus delta X, and then we have Y Then we have a change in y, y plus delta y. And just note that we did put, we reset the axes right over here, and then we'll add the alpha in later just so that it is more simple for the time being. Great, so the second step is to apply the conservation of mass. So let's recall, the conservation of mass, whether it's the system or the shell, it's the same. It's essentially the rate of accumulation, right? And then we have the rate that the mass enters the shell. We have subtracting the rate that the mass leaves the shell. And then we also have the rate of production of mass in this shell. So we're only interested in looking at the steady state solution. So we know that the accumulation is 0, right? And additionally, we don't have any production occurring in this system. So that's also 0. Great. So we have this simplified over here. 0 equals rate in minus rate out. This is something we've been seeing a lot. Now it's just applied to a specific shell. Great. So we have our shell right over here. We have our conservation of mass statement. Well, let's start by understanding how the mass is flowing through our shell. So we have our mass rate in right over here on the left, and then it's going down, remember, at an incline, but we're going to not account for that right now. And then we have it going out on the x plus delta x right over here. So that means if we put it into the conservation of mass statement, it'll look like this, right? Don't be intimidated. This is just right over here. We pulled the width times delta y out, right? That's the cross-sectional area of flow. We have width W as defined in the problem statement, right? So we have width times delta y, and we have right over here, rho times velocity minus rho times velocity at the positions. Great. And then now this is a recall from earlier, maybe the first or second week of this course. We talked about how to actually derive that, and you do that by dividing by the shell volume, right? When in this case, it's width times delta x times delta y, which is correct, right? We have delta x right here, delta y right here, we have width right here. So that is the area, or the volume of the shell. And then we're taking the limit, right? We want to make this infinitely small. So we're going to be taking the limit. And that gives us this expression right over here. And because we also know we see a rho term right here, we know that the density of blood is constant. Constant rho could be any fluid. It's given if the problem gives that rho is constant. We can simplify this right over here to this expression. So what does this expression actually mean? Well, it's the continuity equation for parallel flow. So it means that the velocity doesn't change with the x position. So that's important because we need to know that at this point or this point, the velocity is still the same, right? We have that continuous flow. Great. So now let's move on to the third step. So now we're going to be applying the conservation of momentum. This is where it gets a little tricky. So please pay close attention to this part. Great. So here is the conservation of momentum statement. Again, it is so similar except the shell part. It's the same conservation statement regardless of its entire system, a shell, whatever we're looking at. So we have the rate of accumulation of the x momentum, and then we have the rate that the x momentum enters the shell, rate that it leaves the shell, and then the production of the x momentum. Great. So we also know that the rate of accumulation is 0. Now we're going to be first taking a look at the rate that the x momentum enters the shell. Great, so let's take a look. These two terms compose the rate that the x momentum enters the shell. So let's take a look at the top part. We have the rate that the momentum enters the shell by bulk fluid transport. So that's bulk flow, right? At x. At x, keep that in mind. So we know this. This is rho times velocity times cross-sectional area at x. These are all things that we've done before. This should feel comfortable to you. And then now here is the new part, right? because we're also looking at microscopic flow, we need to also put in this term, the rate that the x momentum enters a shell through molecular transport at y, right? And that is the product of, we have our tau yx times that same cross-sectional area, but delta x, right? There will be an image later and I'll kind of re-emphasize this over there. So these two terms compose of the rate that the x momentum enters the shell. Great, now let's take a look at this next term right over here, the rate that the x momentum leaves the shell. Well, as we can see, it's very similar to the rate that it enters, but we can see we actually accounted for the exit area, right? Location. X plus delta x, if we remember that box we saw earlier, right? X plus delta x is on this, the right side of the face of the box. So again, we have rho times velocity times cross-sectional area at the x plus delta x. So this is something we know through bulk flow. Now over here is where it's through molecular transport. We have the rate that the momentum leaves the shell by molecular transport at y plus delta y. So that's at the top of the box, right? And we have tau yx times the cross-sectional area. And then we have at the location y plus delta y. Great, so combining both of these terms, we have it right here. Again, don't be intimidated. It's again, we just pulled out that cross-sectional area to make the term a little bit shorter, but we have it at y. We have y plus delta y minus sign because right here, we have the rate that it enters and leaves. And that's the same for the velocity right over here, velocity squared, and then at this position times the cross-sectional area, also with rho, right? This rho term. Great. And let's reemphasize again, this term is through molecular transport. And this term over here is through bulk flow. Great. Now let's take a look at the rate of production of momentum, x momentum in the shell. So we know that the rate of production of x momentum in this fluid or this shell, right, is the sum of forces applied in the x direction to the element. So let's talk about what kind of forces we do have in this shell. So initially, we have our gravitational force in the x direction. So right over here, we have mg x. We know this is gravitational force. And we know mass is defined through this, the rho times the volume, right, of our shell. And then lastly, we have gravity right here in the x component, right? Because we redefined this box. It's not at an angle right now. We redefined the coordinates. So that means we know that the actual gravitational component in the x direction is actually gravity times sine alpha, right? Through trigonometry. Now, another force that we do have here in our shell is pressure. Right, so we have the net pressure force defined in the x direction as the pressure on this side, right, of the x, and then opposing on this side, right over here. And we also know from the earlier question that, the earlier definition of the problem, that pressure is independent of x, and also that pressure at the ends of the shell are equal, so the net pressure force is 0. So this was given to us. So therefore, this term is equal to 0. So this is still, you should keep this in mind that this force does exist, but the net pressure force is 0. It's not that there's no pressure. Great, so we have our gravitational force in the x direction, which we determined earlier. We have our definition of the x component of gravity. That brings us to the rate of production of the x momentum in the fluid element is simply just rho gravity sine alpha times the volume, right? So let's put that back in our conservation of momentum statement right over here. So we added that right there. Great, now here's the image I was talking about earlier. We have right here, we have our mass flow, and then we have our molecular transport right over here. We can see tau times the cross-sectional area right here. And then we have tau over here times the cross-sectional area at these two positions. So when we have our term, we have our molecular transport term, we have our bulk flow term, And then we also have our generation, or also this is just the gravitational force term, right? So one thing to keep in mind is we said earlier that mass flow in, the rate of mass flow in is equal to the rate of mass flow out. Well, what does that mean? That means that this term essentially is zero, right? If they equal each other, they will equal to zero. So we can neglect these terms right over here, and it will simplify our conservation of momentum statement to this. So we just took out the bulk flow term, right? Great. So the next step over here, again, is to take, first divide, right? First divide by the area, the shell volume, width times delta x times delta y. This is a simplified right over here, but we're dividing by this entire term, right? That's why it's not over here. So this entire thing is divided by the volume, and then we also take the limit of our shell, right? We want that volume to approach zero, infinitely small. We're looking at a microscopic approach. So as we take the limit, then simply the equation is, if you do the math for this, you get this statement right here. So we have the derivative of shear stress with respect to y is equal to rho g sine alpha. Great. And we're not done here. We're now trying to find tau, right? We're trying to find shear stress. So here's that again from the previous slide. This is where we start doing our ODEs, right? Or ordinary differential equations. So we're going to integrate this, right? By moving the dy over, taking the integral of both sides. We all know how to do this. And we have a constant. We know that we will get a constant. So how do we actually solve for the constant? Well, we apply our boundary conditions. This is not to be confused with the next step where we do apply more boundary conditions, but this is through boundary conditions of our system and our shell. So right over here, we know shear stress at H is equal to 0, right? This is the gas and liquid interface. From the previous question, we know that the shear stress exerted by the gas on the liquid is negligible. So that's 0. We plug that in, and then we solve for C1 to determine this. And then we actually plug it back into our expression to get this statement right here. And this is actually our shear stress distribution right over here. And it's this graph on the right side for you. So you can see that the shear stress is actually linear. It goes from 0 all the way to negative rho gh sine alpha. And this is at 0, position 0. And then this is at H, which is the liquid gas interface, which makes sense. Great. We also know that this is the same expression for Newtonian and non-Newtonian fluids. We didn't specify anything about the type of the fluid and deriving this relationship, meaning that this expression, you'll still get this expression for Newtonian and non-Newtonian fluids. Okay, now let's move on to step number 4. So this is where we apply the relevant fluid constitutive relation. Great, so we know our shear stress distribution right over here. This is from earlier, from the previous step. And we also know, because we're assuming that this is a Newtonian fluid, we're going to be using Newton's law of viscosity. We know our constitutive equations already. So we're going to be using this. And essentially you can see the shear stresses are equal. We set these two terms equal to each other like this. That is step number 4. Simple step. Great. Now let's move on to step number 5. This is where we compute the velocity profile using our appropriate boundary conditions. So this step uses boundary conditions as well. So we have this from the previous slides. Right over here, we have our shear stress distribution. We have our Newton's law of viscosity. And then we divide the entire thing by mu, and then we integrate over here, this term with respect to y, giving us Vx. This is our velocity profile, but we have C2. We need to solve for C2. Constant of integration. Great, so this is just copied over from the previous slide. And then we actually apply the no slip boundary condition, right? At y equals 0, not h, all the way at 0. This is 0. We have velocity is 0 by the no slip condition, meaning that C2 is 0. Great. So that means we actually found our velocity profile, which is given right over here. And you might be wondering, oh, where's the h squared coming out of? It's just they pulled it out. Okay. They pulled out negative h squared from here, which results in this term, this expression. Great. And now we have our velocity profile. We have our velocity profile graphed over here. And right away, we can see we have our maximum velocity at y over h equals 1, which means y equals h. At the top of our flow, we have the maximum velocity. And our maximum velocity is given right over here. And so this is also specific for Newtonian fluids, especially because of that constitutive equation we used in step 4. This is specific for Newtonian fluids. Great, so we have our maximum velocity Vmax, which is this. And we know that because at y over h, y equals h, which is 1, right at the top of our flow, because that's at that gas and liquid interface. Great, now finally we made it to step 6. We have compute the flow rate Q, compute the wall shear stress tau, we already did. And then we have compute the maximum velocity Vmax, which we did. So all we have left is flow rate. Great, so we have our velocity profile and we know the average velocity is this, right? This is how we calculate average velocity. So in the end, we're just plugging in Vx and we're taking the integral, you can do the math on your own, but then we get our average velocity term. Well, we need our average velocity term to be able to actually compute our flow rate Q. So we have our average velocity right here, and we know Q, right? QV, volumetric flow, is our average velocity times width times height, right? So we know our volumetric flow rate is this term right over here after plugging in our average velocity into Q. Great, so we just determined the volumetric flow rate. So let's review our summary. Step 1 is to select an appropriate fluid shell. That is always the first step. The second step is to apply the conservation of mass to fluid and shell. And we're just confirming, right, that we get this continuity equation for parallel flow. We know that the velocity isn't changing in the x direction, right? Then our third step is to apply the conservation of momentum to the fluid and the shell. This allows us to determine our shear stress distribution, right? Step 4 is to apply the relevant fluid constitutive relation, right? Is it Newtonian, non-Newtonian? Step 5, then we computed the velocity profile using appropriate boundary conditions. We have our velocity profile right over here, and we have our maximum velocity. We determined it through these 2 steps. Then lastly, we were able to compute the flow rate. These were already computed. So flow rate, we had to find the average velocity, then we were able to find the volumetric flow rate. Great, so this is just for the example for rectangular coordinates. Now we're going to be going into cylindrical coordinates. Great, so here's our second example. So this is fluid flow through a circular tube, and we have the tube right over here. Let's go over what the conditions of this problem are. First, we're assuming that it is a Newtonian fluid. And the second, we're going to neglect pressure variations caused by gravitational effects. That's the key word right there. Great, we also know flow is laminar and parallel. We have parallel flow. Great. So we know from our shell balance approach, our first step is to select an appropriate fluid shell. So we have our portion of our tube right over here. So in our shell, we're going to have it kind of a two circles with different radiuses. We have the change in delta R and we have the change in delta Z right over here, because one, we have fluid flowing in the Z direction this way. And then we also have our Z momentum traveling in the R direction through molecular transport. So it's kind of important to define our shell correctly here. Great, and we'll kind of go over this as we go along the many steps. Great, so the second step is to apply the conservation of mass to the fluid in the shell. So let's start with our conservation of mass statement. Once again, we have rate of accumulation, rate of mass, rate that mass leaves, enters and leaves, and the rate of production. Again, we don't have any accumulation, it's steady state, and we do not have production either, simplifying the conservation of mass statement this way. Great, so now looking at our shell, we have a rate that the mass enters and the rate that the mass leaves. This is defined as something we do know right over here. We have our rho and velocity at the Z position right over here, Z, this is Z. And then we have minus rho, V, we have velocity at the Z plus delta Z position, which is right over here. And then we also have both terms multiplied by the area, or the area of flow, right? The cross-sectional area. Great. So then we take the limit once again. We want this essentially to be so infinitely small. We want this shell to be infinitely small. So we first divide by the area, right? Or sorry, not the area, the volume. We divide by the volume. We have delta Z right over here. We divide by the volume of the entire shell. And then we take the limit as R goes to 0 and Z goes to 0. We want that to be infinitely small. And that gives us this expression right over here. We know the fluid has constant density from the problem. So we know change in velocity over change in the Z direction is equal to 0. And once again, this is an important result, the continuity equation. We are determining that velocity doesn't change with Z position. So the velocity over here is the same over here, regardless of the Z position. That is great. Awesome. So let's move on. So step number 3 is to apply the conservation of momentum to the fluid in the shell. So here is our conservation of momentum statement. We have the rate of accumulation of the Z momentum, and then we have the rate that the momentum enters and leaves the shell, and then we also have the rate of production of the Z momentum. Once again, we do not have a rate of accumulation for the Z momentum, and then we have right over here, let's start with the rate that the Z momentum enters the shell. So similarly, as the rectangular coordinates, we have two terms. We have bulk flow, bulk fluid transport at Z, and then we also have molecular transport at R. And this is something we know. We have rho times velocity times cross-sectional area at Z. And then we also have tau, shear stress, times we have our 2 pi R delta Z, which is also the cross-sectional area that this is flowing in, right? And then we also have at position R. Great. And then now for the momentum, the rate momentum that leaves the shell, it's similar. We have the rate momentum leaves by bulk flow, bulk fluid transport, bulk flow at Z plus delta Z. And then we have the rate that the Z momentum leaves by molecular transport at R plus delta R. And we have these right here, rho V, V, and then cross-sectional area at Z plus delta Z. And then we have tau times cross-sectional area at R plus delta R. Great, so putting that back into our conservation of momentum statement, once again, to solidify our understanding, we have molecular transport terms right over here, and then we have our bulk flow terms right over here. Next, let's move into the rate of production of the Z momentum in the shell. So similarly as the previous, we have the rate of production of Z momentum in the fluid element for the shell is the sum of forces applied in the Z direction to the fluid element. So the gravitational force in the Z direction in this case is actually 0 because the tube is horizontal the gravitational force in the z direction is 0. It also mentioned that pressure due to gravitational force is negligible. So that is that. And then we have the net pressure force in the z direction. We don't know that the opposing forces are equal this time. We weren't given that. So we have P, right, as z on this side, put it going this way. And then we have the pressure at this position going the opposite way, right, times that area, cross-sectional area. Great. So therefore, our rate of production is just this net pressure force term, not the gravitational force. And then we're going to put that back into our conservation of momentum statement right over here. And then we're going to now take a look at simplifying this. Once again, we have our mass flow. This is mass flow, right? Mass flow in, mass flow out, mass rate flow out. And then we have this term right over here, right? And we have our molecular transport. We have our pressure, net pressure force. So once again, we defined that first, it's steady state. The mass rate in is equal to mass rate out. Therefore, this term goes to 0, right? So we can simplify this in a more easier way right over here. The next step, as always, is to divide by the shell volume, which is right here, right? So we're going to divide by the shell volume. And then we're going to take the limit. We want that shell to become infinitely small, right? So we're going to take the limit as r goes to 0, as z goes to 0. And then we will find, so this is right here, same thing from the previous slide. This is all math, so I suggest taking your own time to make sure that this checks out. Then it simplifies into this expression right over here. So this can be simplified to our z momentum equation right over here. And now it says that essentially this, our differential equation, we have a function of r that's equal to a function of z. And we know that this can only be true if both functions equal some constant c1. So let's put that c1 in there. So we know we need to find c1. So this term is from the previous slide right over here, right? This right-hand side, we're going to find c1. So we have dp over dz and the negative. We're going to integrate this ordinary differential equation. That gives us this expression right up here, right? We're going to move the dz over here, integrate it, and then we have c1, c2, and this is where we apply our boundary conditions. We know at length 0, it's pressure 0, and at length L, we have pressure L. We're going to be then finding C1 and C2. When you do the math, these are the constants you do get. So coefficients, sorry, it's the coefficients you get. With this, we're going to be able to use the C1 coefficient. We don't really need the C2 coefficient. We still need this specific expression. We're going to use the C1 constant, plug it back into here, and solve for tau, right? Remember, this step is all about tau. We need to be aware of what we're trying to solve for and not getting too lost in a different direction, right? We're looking for tau. We're looking for the shear stress distribution. So let's do that. We just put this back into C1. Now we're looking at the left-hand side of the statement. Then, if you do the math, this is the expression that you get. This is your shear stress distribution, but we have another C3 over here. We have a constant here, right? Coefficient. So what now? So we have this, but the thing is, we know that the net momentum flux at the center is 0. So if we have 0, that means C3 is 0 as well. But if there's a solid object at the center, any solid object in your pipe, in your cylinder, right, then C3 cannot equal 0. There will be momentum flux at that point. So this is something really to keep in mind. Luckily, in our question, we didn't have any object, so we know C3 is 0. That simplifies our expression to this. So this term cancels out. We just move the 2 back in. So we have this as our shear stress distribution. Great. And we also know that shear stress is maximum at the wall. Radius equals cap big R, right? So all we do to find the maximum shear stress is to plug in big R, and this is our maximum shear stress of our system. Great, now let's go to step number 4. We're going to apply the relevant fluid constitutive equation or relation, sorry. So we have our shear stress distribution from the previous step. And then now, again, we're going to use the constitutive equation, the Newton's law of viscosity, because this fluid is Newtonian, which is right over here. And again, the taus, we can set them equal, these two terms equal to each other like this. Great, and that's step number 4. Again, very simple. And the trick is just making sure you're doing it right? Ensuring that you know what type of fluid this is. Great, so step number 5 is to compute the velocity profile using appropriate boundary conditions once again. So we have this expression from the previous step, setting equal to Newton's law of viscosity, and we have shear stress distribution right here on the left-hand side. Then we're going to divide the entire term expression by negative mu, integrate, and then remember right here, integrate, solve for VZ, right? Velocity profile, remember what we're looking for. And then we have this expression right here. Again, we have C4, we have another coefficient. Great, so what do we do with this coefficient? Well, we're going to keep going. We know that there's a no-slip boundary condition at R equals R. At the wall, we know velocity is going to be 0. So we plug in 0 here, and then we solve for C4 to get this coefficient, right? And then we plug C4 back into the expression to get our actual velocity profile right over here. Great. So we have our velocity profile, and we also know our maximum velocity is in the center of flow. We have a parabolic velocity profile. So we know at R equals 0, which is the center of our cylinder tube, we know V max is equal to this, delta P times radius squared over 4 mu L. Great, now let's go to our final step, which is step number 6. We're going to compute the flow rate, the wall shear stress, we already did, and maximum velocity V max, which we already did as well. So we need to find flow rate. And again, to find flow rate, we need to first find average velocity. This is how we find average velocity. We plug in our velocity profile into this average velocity expression, and then we solve for average velocity. And then now the last step is, once again, we have our average velocity, we have our volumetric flow, Q, right, flow rate, and then simply we're going to plug our average velocity in, and then we get our volumetric flow rate right over here. And lastly, this is an important result right over here. We have the Hagen-Poiseuille equation. So it's QV is equal to pi delta P R to the 4th power over 8 mu L. And this defines the volumetric flow of a Newtonian fluid, keep in mind Newtonian fluid, through a cylindrical tube. Great, so let's do a final summary of the shell balance approach for cylindrical coordinates. We have step 1 is to select an appropriate fluid shell, which we did, delta Z, delta R. Then we applied the conservation of mass to the shell, and we determined that velocity does not change based on the Z direction, rather in the R direction, right? We applied the conservation of momentum to the fluid in the shell, and we determined the shear stress distribution this way. Then we applied the relevant fluid constitutive relation. The fluid was Newtonian, so we applied Newton's law of viscosity. Then we computed the velocity profile, and we used our boundary conditions to determine our velocity profile and maximum velocity. Lastly, we computed flow rate. We already computed shear stress and maximum velocity, and we determined the volumetric flow rate is as follows. So these are the steps for the shell balance approach. And if you have any questions, please come to my office hours. I'm more than happy to help, or send me an email. I hope that this was helpful for you all, and I wish you best of luck and a happy break. Thanks for watching.